everyone. Today again I am continuing with the old topic kinetics of complex reactions. In my previous video we have already done the derivation of opposing reactions. We have done K1 is equal to Xc by At ln of Xe by Xc minus X. This derivation we have already done in my previous video. Kindly watch it so that you can have a better connectivity. I am going further. From here, I am going to the next step. If the values of Xe, X and T are known, the value of K1 can be calculated. The concentration of X can be determined at different times before reaching the equilibrium to get the value of X. Value of Xe can be obtained by measuring the concentration of X, that is the products, after attaining equilibrium. Further, value of K2 that is this one can be calculated by substituting the values of K1, A and Xe. Now, from this equilibrium, reactant A going to product X with at equilibriums K1 and K2. We have the equation K1 A minus X is equal to K2 Xe. That means we can say when we open the bracket K1A minus K1X. So K1 Xe. K1A minus K1Xe. So K1Xe and K2Xe can be brought as common. That is Xe we can take out as common. So what we have now is K1A is equal to, if I take it on this side, the negative symbol will become plus. So it will be K1 plus K2 of Xe times Xe. Now this can be further written like this. K1 by K1 plus K2 is equal to Xe divided by A. Now we have the value of Xe by A. This value of Xe by A we can directly substitute over here. Xe by A. So now what we will have is K1, this K1 is equal to Xe by A will be K1 divided by K1 plus K2 times T. So we can write it 1 by T ln of Xe by Xe minus X. There is K1 here, which will get cancelled out. So what we have now is K1 plus K2 is equal to 1 by T ln of Xe by Xe minus X. If you observe this equation carefully, we can say that this equation is similar to the equation for first order reactions, which can be therefore which can be represented as, that is, we can say K1 plus K2. Since it is a first order reaction, we can say K1 plus K2, or we can replace this K1 plus K2 by K. So this can be written, now this K1 plus K2 can be written as K is equal to 1 by T ln of xe by xe minus x. Now xe also can be replaced by a. If we replace xe by a, so we now have a divided by a minus x. Here, when we are arriving at this equation, that is what we have derived so far, here it is assumed that the concentration of the product is 0. If it is not the case, and the initial concentration of A and X are A and X0, the net rate now at time t will be given by the equation dx by dt is equal to K1 A minus X minus K2 X plus X0. Now it can be concluded from this equation that K1 plus K2 is equal to 1 by T ln of K1A minus K2 X0 divided by K1 A minus K2 X0 minus K1 plus K2 of X. The concentration at equilibrium is defined as Xe, concentration at equilibrium, Xe is equal to K1A minus K2X divided by K1 plus K2. So, this above equation further reduces to K1 plus K2 is equal to 1 by T ln of Xe divided by Xe minus X. The muta, so you can say this is our final equation, that the muta rotation of, therefore you can say the muta rotation of alpha D glucose and into beta D glucose is an interesting example of this reversible first order reaction. Alpha glucose going to beta D glucose. One more example is the conversion of gamma hydro, just a minute, butyric acid. Gamma hydroxy butyric acid to lactone. It is another very good example. One more conversion of simplest one, conversion of ammonium cyanate NH4CNO to urea. H2NCONH2. This is ammonium cyanate into urea. So these are the different examples which undergo these opposing kind of reactions. They will undergo first order reactions. Next is parallel reactions. This all derivation was incomplete for earlier reaction, that is the opposing reactions that we have done. It is a continuity of opposing reactions. The next one that I'm going to upload a video is on parallel reactions. Here I am concluding this video. Do continue with the next playlist. Thanks for watching.